Hi everyone, my name is Masanori Misono. Today I will talk about our research, DMAFV, testing device drivers against DMA faults. First, let me introduce the background of our research. Device drivers interact with devices in several ways. PIO, port mapped I/O, and MMIO, memory mapped I/O, are used to access device drivers registers. In addition to PIO and MMIO, DMA, direct memory access, is used to exchange data between a device driver and a device. DMA transfers data directly without involving a CPU. Therefore, it enables high-speed data transfer without increasing the load of the CPU. On the other hand, devices do not operate correctly always. For example, hardware failures are inevitable, and a device may produce invalid values due to malfunction. In addition, in recent years, there have been reports of devices that operate maliciously. These malicious devices produce anomaly values intentionally and try to compromise device drivers. Therefore, it is important for device drivers to validate values from devices. However, several studies showed that many device drivers implicitly assume that devices always operate correctly and often do not sufficiently check device input values. To find these problematic code in device drivers, there are several existing studies. One of the main approaches is utilizing static analysis and symbolic execution. The advantage of this approach is no need for actual device to test. However, these approaches require source code, and it also often suffers from many false positives. Alternatively, there is an in-kernel page fault-based fault injection scheme to test device drivers. In this approach, the in-kernel fault injector detects the memory region used by device drivers by incorporating a kernel's device API. The fault injection modifies the page table to cause a page fault when a device driver accesses that memory to read values from devices. Then the fault injector performs fault injection and see if device drivers handles anomaly device inputs correctly. This approach achieves fine-grained monitoring and supports testing both MMIO and DMA regions by cooperating with the kernel APIs. However, this approach is always dependent as it relies on kernel APIs. Other study proposed hypervisor-based fault injection to inspect the device driver's error handling process. The hypervisor traps a guest device access and performs fault injection. This approach is always independent and does not require source code. However, the previous studies only test PIO and MMIO regions, and testing the DMA regions is not supported. Hypervisor can trap PIO accesses by intercepting IO instructions issued by a guest. Also, a hypervisor can detect the MMIO regions by converting the device's PCIe configuration space, and then trap MMIO accesses by utilizing nested paging. However, the information of the DMA region used by device is not stored in PCIe configuration space. Therefore, hypervisor cannot detect DMA region easily, and testing DMA area was not supported in these studies. In this study, we propose a novel way to test device drivers against DMA faults using hypervisor-based fault injection. The key insight of our approach is device holds DMA region information in its registers to perform DMA. Therefore, one can detect the DMA region by consulting these registers. This is the overview of the proposed method. In the proposed method, we run device drivers to test on a thin hypervisor. Unlike traditional hypervisors, this hypervisor does not virtualize entire hardware and only is used for fault injection. To test device drivers, first, the hypervisor detects DMA region used by device driver by consulting its registers. Then the hypervisor configures nested paging to cause nested page faults when the device drivers access the DMA region. And the hypervisor performs fault injection when trapping the access. As a specific example, I explain how to identify the NVMe device DMA area. NVMe is the next generation communication standard. NVMe devices use several DMA-based command queues as control plane. One of the main command queue is admin command queue, ACQ for short. The addresses of the ACQ is stored in ACQ-based address registers, and the ACQ address base register is in the NVMe's MMIO region. Therefore, by consulting the ACQ-based register, the hypervisor can detect the DMA region that is used by NVMe and NVMe device drivers. We implement the prototype of DMAFV. We use Bitvisor as a base hypervisor, and we choose NVMe as a target device. We implement the NVMe's command queue detector and fault injection scheme in the hypervisor. We test the Linux NVMe device driver using the proposed method. We use Linux 420, and we perform fault injection during loading and unloading NVMe device drivers. The proposed method found one kernel panic bug. We investigate the bug, and we found a null pointer reference bug in a function that handled command message from our NVMe devices. The right side shows the excerpt from the source code. In the source code, CQE command ID is the input from a device. Bulk MQ tag to RQ function returns null if the command ID is invalid. However, this function does not check the return value from the bulk MQ tag to RQ, and therefore null pointer difference occurs. The red square indicates the required fix. We reported this bug to a maintainer, and it was confirmed. Later, this bug was fixed. To investigate the runtime overhead of our proposed method, we measured the I/O throughput and latency of the NVMe using FIO. The left side shows the read mean I/O numbers per second. As shown in the figure, the overhead of our proposed method was about 500 IOPS. The right side shows the read latency, and the overhead of the proposed method is several tens to hundreds of milliseconds. We think the results are considered sufficient for practical use of this method. The low overhead is important because some device drivers will time out if there is no response from the device for a certain period of time. Furthermore, by making the test test environment close to real environment, bugs induced by subtle timing due to interrupts would also be reproduced in the proposed method. Other future works, one of the main challenges is automatic generation of DMA region detection code. One possible approach is observing device drivers' behavior in the hypervisor and detecting its DMA region. One method is always independent. Therefore, we also think applying one method to other OSs and hypervisor device drivers. This is a summary of these presentations. Checking values from devices in device drivers are crucial for security. However, existing methods lack always independent DMA value tests. We propose DMAFV, a novel way to test device drivers against DMA faults. DMAFV detects DMA region by converting devices' registers and then perform hypervisor-based fault injection. We implement a prototype and test Linux NV driver. We found an important difference bug in the function that handles command messages from a device. That's all. Thanks for listening.